Now, the most common situation when you use this acceleration to work out mass is when you have something heavy and you've got objects moving in circles around it. Now, in this case, it's something moving. That means it might start off with a vector like this, end up with a vector like that. Look at the difference. This turns into that. So the acceleration is towards the middle. So whenever you see something moving in a uniform speed in a circle, there must be an acceleration towards the middle. That's called centripetal force. And it's given by the equation force equals mv squared over r, where this is r, the radius of the circle it's travelling in, v is how fast it's moving, and m is the mass. So let's consider a situation when something is observed to be moving in a circle around a mass. So we know that this is the force, and we know that is supplied by gravity. So this must equal g m over r squared, where m is the mass of, big M is the mass of this thing here, small m is the mass of that one. So we cancel out the small masses, cancel out one of the r's, and we find that if you want to work out the velocity, for example, v squared equals gm over r, or if you want to work out the mass, m equals rv squared over g. You can rearrange that, so v equals root gm over r. So what that indicates is, if there's a mass somewhere and things are moving in circles, the bigger the mass, the faster it goes. But also, as the r gets larger, the velocity should go down. So if you plot velocity against distance, you should get a curve that proportional to 1 over root r, which will look something like this. Things get slower as they go further out. And indeed, that's what you see. Here's a simulation. What I've got here is I've put an invisible mass in the middle with a whole bunch of simulated particles obeying this equation, and what you can see is the ones in the middle, we can zoom in if you like, are going fast, whereas the ones further out are going slower. So this is what you would normally expect to see for things moving in circles around an unknown mass. We've seen that if a galaxy only had all its mass in the middle, so let's say here was a galaxy, but virtually all the mass was, say, in a giant black hole in the center, then if we plot velocity versus distance, we should get velocity equals root g m over r, which will look something like this going down. But that's not actually very realistic. Galaxies do have big black holes in the middle, but these black holes are about, at most, 10 to the 8 solar masses, whereas the overall galaxy is more like 10 to the 11 solar masses. So this is much bigger than that. Most of the mass is not the black hole, it's the vast numbers of stars orbiting around. And that makes it a bit tricky to calculate the gravity, because the stars are not all in the same place. So if we had, say, a little gas cloud out here, and we're trying to work out what the acceleration on it is, and hence how fast it will move, we can't, what do we use for r? We can't just assume it's at that distance from the mass, because it's at that distance from some of the mass, but it's at this distance from other bits, and that distance for other bits yet. So what can you do in a situation like this? Well, luckily for us, there is a simplification we can make, originally worked out by Isaac Newton. Let's say you do have some galaxy like this, and let's say you're trying to work out the motion of something, maybe a gas cloud here. It turns out mathematically, what you can do is make an imaginary sphere around the center of the galaxy of radius how far out your test particle, your gas cloud, is. All the mass that's inside this radius, you can approximate it as just being a lump in the middle. And then all the mass that's outside, you can ignore. So that's the trick. Draw a sphere of radius r. Move all the mass inside within the sphere to the point in the center. All the mass outside, you ignore. Now this trick is seriously useful. I should mention it's not precisely accurate. It is precisely accurate if galaxies were spherical. As most galaxies are flattened, it's not spot on, but it's pretty good. So what now would you expect to see as you move out? Well, let's say you have something very close to the center. In this case, r is very small. V equals root g m over r still, but m is just the mass inside the sphere. So r is very small, but m is smaller still because there's basically very little mass in here. So that means at the center, speed is actually very low, which kind of makes sense. If you're in the middle of a galaxy, there's equal amount of mass in every direction, so you won't be going anywhere. You're being pulled the same way in every direction. As you go out, say to here, now your sphere is larger, which means the mass has got bigger. R has also gone up, but normally the mass goes up by more, so the speed goes up. Eventually you get to the edge of the galaxy, and now your sphere includes all the mass in the galaxy, so that's now the mass of the whole, all the stars in the galaxy. So that's probably about where you're going to get your peak velocity. And then when you go further out still, say over here, R has got larger. M can't get any larger because you've already got all the stars inside. So now it starts behaving like 1 over root r, as you expect. So this is called a galaxy rotation curve. And you expect it to be 0 in the middle. Have a peak somewhere near where the stars run out. Maybe a little bit inside, depending how smoothly they run out. And then to drop off as 1 over root r when you go further out. That's what we expect.